Chapter 8, DC Circuits. After completing this chapter, the student will be able to solve for all unknown values, current, voltage, resistance, and power in a series, parallel, or series parallel circuit. Understand the importance of voltage dividers. Design and solve for all unknown values in a voltage divider circuit. First type of circuit that we're going to talk about is the series circuit. This is somewhat of a review because we've already talked about the series circuit and how it relates to resistance and how it relates to power. So this really should be a review. By definition, a series circuit is a circuit that provides only one path for current to flow. Factors governing the operation of a series circuit is that the same current flows through each component, meaning total current, I sub T, is equal to I sub R1 is equal to I sub R2 equal to I sub R3 equal to I sub R to the nth degree. What it really means is there's only one path for current to flow into. It must complete that path. There's no place else for it to go to. That's a very important concept as a technician when you're troubleshooting a piece of equipment. If you know it's a series circuit and you know how much current is going into that, there's only one way in and one way out. If you're measuring a difference, like you put 10 amps in and you're only getting 8 amps out, 2 amps must be going somewhere. That's your problem. That's what you have to find, where that current is going. So this is a very, very important troubleshooting tool. People always want to use screwdrivers and wrenches and pliers to work on things. Not me. I like using a formula like this because it'll really help you analyze a problem before you break out your tools and start disassembling something. In a series circuit, the total resistance is equal to the sum of the individual resistances. As you stated earlier, everything has resistance. So as you put different components together in series with each other, we begin to add that resistance up. The other thing I want you to remember with this formula here, where total resistance is equal to R1 plus R2 plus R3, is not only resistance of components, but also the resistance of electrical connectors and terminations. It could also be the resistance of a bad solder joint. It's all additive. So if you come up with a total resistance or you have a value of total resistance that is other than what it should be, it might be because of bad connectors, terminations, bad solder joints. On our next slide here, we see the total voltage across the series circuit is equal to the sum of the individual voltage drops. Total voltage is equal to ER1 plus E sub R2 plus E sub R3 plus E sub R to the nth. The two very most important things you need to remember about a series circuit is that current is constant in a series circuit, and that a series circuit is also known as a voltage divider. And that's exactly what we're doing here. We're dividing this voltage up. This voltage, 1 plus 2 plus 3, has to equal total. It has to. Again, that is probably one of the most powerful tools that you could use in the analysis of a series circuit. These numbers must equal the total. Another term that the book uses is that voltage rise. Voltage rise must equal voltage drop inside a circuit. The voltage drop across a resistor in a series circuit is proportional to the size of the resistor. The bigger the resistance, the bigger the voltage drop. The smaller the resistance, the smaller the voltage drop. And also we know that I is equal to E over R, so that when resistance increases, current's going to decrease. And when resistance decreases, current will increase. That is an inverse proportional relationship between resistance and current in a circuit. And then finally, for series circuit, This is what we talked about in Chapter 7, power, right? Power total is additive. Piece of T is equal to piece of R1 plus piece of R2 plus piece of R3, etc., plus piece of R to the nth degree. Power is strictly additive. Always has been, hopefully, probably always will be. Our next slide shows us a schematic diagram of a series circuit. And what we see here is that current flows negative to positive, so the current here will be flowing in a counterclockwise direction through this circuit. First it flows through R3, then it flows through R1, then it flows through R2, then it flows through R1. What happens when current encounters the resistance of R3, it's going to develop a voltage drop. When current continues and hits R2, it's going to develop another voltage drop. When current continues and encounters R1, it's going to develop another voltage drop. This voltage drop plus this voltage drop plus this voltage drop will have to equal this voltage rise or the source voltage. It has to. Question? Okay, this is out of the lab book.
Yeah.
Okay.
I did just recent and it equals like it comes up to 1981.
That's because of rounding errors. Rounding errors.
Would mean it's correct.
Yeah, I would say it's correct. Just the only thing that you could do with that is because again it's the rounding that you're doing. What I recommend that you do is let me grab a marker here. When you're dealing with a number, let's say it's 32476.391. What I recommend you do for rounding is put this in the most common terms, okay? So this will be 32.47, and then I want you to round this if this here, so this is a 3, so this will stay a 6. Kilo units. Okay? And generally speaking, if you pay attention, to that, you'll get much more accurate answers. These answers are very general, but by the time you get to your third quadrant here, we want you to be a lot more specific. The other thing is, this is my minimum rule on rounding. Okay? What I would recommend that you do, if you can, is try to keep the numbers as accurate as possible by storing them in your calculator memory and then going back and using the actual whole number before it was rounded. And then you're going to see your answers are going to get much closer. But no, that's within specifications. Good question. Thanks for asking. When you're analyzing a series circuit, this is the process that you should use to solve for values in a circuit in order. First, find the total resistance. Once you know the total resistance and you know the total voltage, then you could determine the total circuit current. I is equal to V over R. Then you could determine the voltage drops and dissipation. The voltage drops and dissipation. How much current is encountering each resistance and what size voltage drop is it creating. In parallel circuits, these are circuits having more than one current path. Factors governing the operation are the same voltage exists across the branch of the parallel circuit and is equal to that of the voltage source. Total voltage is equal to voltage of resistance 1 plus the voltage drop of resistance 2 plus the voltage drop of resistance 3. Voltage rise has to equal voltage drop. Has to. So since the voltage rise here is applied in parallel across all these voltage drops, they've got to be the same. In a series circuit, the most important thing was that current is constant through a series circuit. The most important thing about a parallel circuit is that voltage is constant across a parallel network. The current through each branch of a parallel circuit is inversely proportional to the amount of resistance of the branch. Same formula applies. I is equal to E over R. If the resistance increases, the current through that branch is going to decrease. If the resistance in that branch decreases, the current through that branch will increase. There's an inverse proportional relationship between the two. Does that make sense? The total current in a parallel circuit is the sum of the individual branch currents. IT is equal to IR1 plus IR2 plus IR3, etc., etc. Series circuits were known as voltage dividers. Parallel circuits are going to be known as current dividers because we're dividing up current. Very good. And that's exactly how I want you to think of these in the future. When I say series circuit, I want you to think voltage divider. When I say parallel circuit, I want you to think current divider. Very good. The reciprocal of the total resistance in a parallel circuit is equal to the sum of the reciprocals of the individual resistances. It's a mouthful. That's a lot to say. Basically, what we're saying here is that total resistance in a parallel circuit is equal to the sum of the reciprocals of the resistance. In actuality, what are we doing here? We're adding up the conductivity of branch 1, the conductivity of branch 2, the conductivity of branch 3, and then we're taking the reciprocal of that, and that gives us our total resistance. The other thing to keep in mind about this is that when you add branches to a parallel circuit, you add resistance, right? But what are you doing to the overall resistance of the circuit? You're decreasing it. By adding resistance, you're decreasing it, because by adding resistive branches, those are also conductive branches. It's like putting another bridge across Lake Washington. If we did that, what would happen to the flow of traffic? It would increase. Would there still be traffic jams and backups and accidents on it? Yeah. But what would it do to the overall flow? It would increase it. That's why this formula works here. Does that make sense to all of you? Okay. And then again here, the total power dissipated in a parallel circuit is equal to the sum of the power consumed by the individual resistances. Power is additive in parallel circuit. Goes back to chapter 7 and what we talked about in power. Power is additive. Our next slide shows us a graphical depiction, a schematic of a parallel circuit. One of the things that I want to focus your attention to are these little dots right here underneath R1, R2. What are these called? Junction or nodes. And this is where business happens, right? This is where current is going to divide. This is a very important troubleshooting tool, again, for technicians. If you know that 10 amps is flowing here, and 2 amps is flowing here, how many amps must be flowing here? 8. If 8 amps are flowing here and 6 are flowing here, how many must be flowing here? 2. So 2 plus 6 equals 8. 8 plus 2 equals 10. 10 amps in, 10 amps out. All amps present and accounted for. And that's what you've got to determine with your test instrument. You get in there, you could monitor that and see where the missing current is. In series parallel circuits, or as I call them, complex circuits, these are circuits that consist of both series and parallel elements. To solve most series parallel circuits, we simply apply laws and rules to each type. In a series, formulas are applied to series portions of the circuit, and parallel formulas are applied to the parallel parts of the circuit. There's no special process. You have to be able to discern whether a circuit is series or whether a circuit is parallel by looking at it. There's no easy way of doing it. You use the series formulas for the series portion and the parallel for the parallel portion. This is an example of a complex circuit. This is a simple example of a complex circuit. We can clearly see here that resistor 2 is in what relationship with resistor 3? It's a parallel. Between this node here and this node here, I like labeling my nodes. On schematic diagrams, I'll label this node A, the top node A, the bottom node B. Between node A and B, how many resistances are there? One. There's two resistors, but there's one resistance. So I'm doing a little bit of wordplay, but there's a difference. Two resistors make up one resistance. That one resistance is in what relationship with R1? It's in series with R1. R1 is in series with the resistance between node A and node B. The resistance between node A and node B is the combination of the resistance R2 in parallel with R3. So once you do that, once you have the ability to look at a circuit and figure that out, that's what we're trying to develop in you. This is very fundamental. This circuit here is very simple. Just like the gentleman that's been working out at the lab bench, I don't know if you saw him out there, the schematic, and it was a tube circuit that he's working on. It's the exact same thing. He's working on complex circuits. He's working on circuits that are exactly like this. So he has to apply the parallel rules to the parallel portion of the circuit and the series rules to the series portion of the circuit. It's that simple. Our next slide discusses voltage dividers. These are circuits used to set up a bias or operating point of various active electronic components. If you want to operate a transistor, you need to properly bias the transistor. If you want an integrated circuit to function properly, you need to bias the integrated circuit. The circuit that we use to set up these bias levels are simple voltage dividers. Well, you know a voltage divider is what? A series circuit. So we use a voltage divider to divide a high voltage to a lower voltage. This process of dividing up the voltage is often referred to as scaling. It's often referred to as scaling. Ohm's law states the current through a circuit is directly proportional to the voltage across the circuit and inversely proportional to the resistance. Therefore, current is equal to voltage divided by resistance. I is equal to E over R. We increase R, we decrease I. We decrease R, we increase I. We increase E, we increase I. We decrease E, we decrease I. So make sure you understand that direct proportional relationship and the inverse proportional relationship between these three properties. Current division is directly proportional to voltage across the circuit. If the voltage increases, the current is going to increase. If the voltage decreases, current's going to decrease. The voltage drop is equal to the percentage of the dropping resistor to the sum of the dropping network, meaning voltage drop is equal to voltage source times the ratio of resistance of the drop as it compares to the resistance total. See what we're doing here is this is a ratio, our drop over our total times the amount of voltage source gives us our voltage drop. You don't have to use this formula if you don't want to. If you understand algebra and you understand numbers, you could use this, it makes it easier. But this doesn't replace Ohm's law. This is just another tool in your box to make it a little bit easier for you to analyze the circuit with. In summary, a series circuit provides only one path for current flow. Series circuit formulas include IT is equal to IR1 equal to IR2 equal to IR3. This is Kirchhoff's law, right? Current is constant in a series circuit. RT is equal to R1 plus R2 plus R3. Resistance is additive in a series circuit. ET is equal to ER1 plus ER2 plus ER3. This basically says that series circuits are also known as voltage dividers. I is equal to E over R. Why? Because Ohm says so. But because of that, we also see the inverse proportional relationship between I and R and the direct proportional relationship between I and E. Power, of course, is additive in a series circuit. A parallel circuit formulas. A parallel circuit is also known as a current divider. Very good. The total resistance of a parallel circuit is equal to the sum of the reciprocals, which basically means we're adding up the conductivity of the different branches. Total voltage is equal to the voltage applied across all the loads. That basically says that voltage is constant across a parallel circuit. I is equal to E over R, and power again is additive in a parallel circuit. Series parallel circuits are solved by using the series formulas for the series parts of the circuit and parallel formulas for the parallel parts of the circuit. Voltage dividers. Voltage dividers are series circuits that we use to divide up voltage, and parallel circuits are circuits that we use up for the purposes of current division. Any questions on anything that we covered in Chapter 8? I do want to add one thing here to Chapter 8 that I don't feel that the book does an adequate job of addressing, and that goes back to what we were talking about as it pertains to voltage dividers. What kind of circuit do we use for a voltage divider? Series circuit. So, I'm going to draw a simple series circuit here on the board with 1, 2, 3 resistors in series with each other. Do you all agree this is a series circuit? Do you all agree that this is a voltage divider? What are we going to use a voltage divider up? What are we going to use a voltage divider for? To reduce the voltage to what values? It's not a trick question. What do we want to divide it up for? To what values? The appropriate values for the device, right? So let's say, for example, I had this problem with my series circuit, and this here was a 24-volt power supply. And these 3 resistors, we have to divide up different appropriate voltages. One very common voltage that we use throughout the electronics industry is 5 volts. Another important value that we use in the industry is 12 volts. 12 volts, okay? So, I'm going to put a couple nodes in the circuit here. If I measure the voltage, this is negative, this is positive. If I measure the voltage between here, this point, let me label these nodes here. I'll put 4 nodes here. One at the top is A, B, C, and D. If I measure the voltage between C and D, I want to get 5 volts. Agree with me? If I measure the voltage between B and D, and I want to get 12 volts, how many volts are going to be across this resistor alone? Very good. This will be 7 volts. See, between here and here is 5. Between here and here is a total of 7. Do you all see that? Does that make sense? Okay. So, how many volts are remaining between A and B? How many? 12. Very good. So, is this a voltage divider right now? Yes, it's a voltage divider. 24 minus 12 minus 7 minus 5 equals 0. Equals 0. What we put in voltage rise equals voltage drop. You all agree with me? Okay. Now, how do we construct a circuit like this? Well, this is the interesting part. This circuit in and of itself is worthless unless we connect loads to this circuit. And what I mean by a load is something that converts electric energy into some other form of energy. A light bulb could be a load. A motor could be a load. So what we're going to do here is we're actually going to connect another load, which we could represent it with a resistor here. And this is going to be a 5-volt load. The load we're going to connect here off of B is going to be a, how many volt load? 12-volt load. And then this up here, we're just going to use this for a voltage divider to get rid of the other 12 volts from the 24 volts. So I'm actually connecting two loads to this circuit. Do you agree with me? Okay. This still doesn't help us design this voltage divider circuit. In order for us to efficiently design this voltage divider circuit, we also have to know what the current requirements of these loads are. This might be a power amplifier in your car. If this is a power amplifier in your car, this thing might be drawing 20 amps. If it was drawing 20 amps, what would the power output of this amplifier be? P is equal to E times I. How many watts would this be capable of? Get your calculator out. How much? 240 what? Watts. Very good. Does that make sense? Okay. Over here, this is 5 volts. This is 5 volts. This might be a satellite radio receiver. Satellite radio receiver, which only draws 500 milliamps. Very small, microelectronics. So, how many loads do we have in the circuit? How many loads do we have in the circuit? 2. And they are the amplifier and the satellite receiver. So what is our total load current in this circuit? Very good. Total load current is going to be 20.5 amps. 20.5 amps. This is where the book leaves you off, because there's some examples of loaded voltage dividers in the book, but the author doesn't really show you how to solve them. The author doesn't even solve them properly. Okay? So what you want to do in a situation when you're developing a circuit like this resistor right here, which is going to start the voltage division process, this divides one, this divides more of the voltage. This is called our bleeder resistor. Our bleeder resistor. And that's the resistor between node C and D. In order for this circuit to operate efficiently, we need to have 1/10 of the total load current flowing through it. So what is 1/10 of 20.5 amps? 2.05 amps is 10% of the total load current. Once we determine this, now we can calculate out how much resistance is going to be required to give us this voltage drop. R is equal to E over I. So 5 divided by 2.05 gives us the amount of resistance of this resistor. If we're going to have 2.05 amps flowing through this resistor, and we've got 500 milliamps flowing through this load, how much current's going to have to be flowing up through this resistor? .05 amps coming up, amps coming up from here. 2.55 amps. Do you all agree with that? I agree with that. Same thing here. We can determine what size resistor this needs to be by R is equal to E over I. If I've got 2.55 amps flowing up through this resistor, and I've got 20 amps flowing up through this load, how much current is going to flow up through this resistor? Very good. 22.55 amps. If 22.55 amps is flowing up and into the positive side of the battery, how much needs to be flowing out of the battery? The same, 22.55. If 22.55 is flowing out of the negative terminal of the battery, 2.05 is flowing up here, 500 milliamps is flowing here, 20 here, it all adds up again. What goes in comes out. Does that make sense? No. That was a very good question. That was the total load current. That's the total, that's this current and this current. This is the bleeder current. So if we look at 20.5 plus 2.05, this is the load current plus the bleeder current. That starts the division process. So this is how I want you to solve for loaded voltage dividers. Your book, the author really doesn't explain. He just kind of pulls some numbers out of the air, and it kind of leaves you hanging there. Any questions on a loaded voltage divider? Trust me, you'll see them again in the future. You'll see them again in the future. So when you get to that lab, I don't know if you've done that lab already, a lot of students have confusion because, again, the author doesn't give you enough background information on it. Okay, that is all I have for Chapter 8.